The quantum mechanics, formal paper of quantum mechanics actually came in 1926, I think, when Schrodinger wrote a paper in Physical Review. So this was a very, very important paper in Physical Review, which actually signaled, most historians think this is the first paper of quantum mechanics, proper quantum mechanics. And many of these postulates and all that evolved. And very next year, actually the chemistry got a big boost. 1927, when Hitler and London produced a paper based on quantum mechanics and what is called the valence bond theory. And that was the genesis of valence bond theory, 1927. Very interesting to read the history. And Niels Bohr actually started talking about it long back, but later on people realized that the Bohr's theory is not correct. Bohr's theory is only right for hydrogen and hydrogen-like atoms. It could not explain. So the angular momentum quantization that Bohr brought in was only a very restricted part of quantum mechanics, and it doesn't explain. So then later on, of course, in this Schrodinger's paper, along with Heisenberg, he actually enumerated the whole quantum mechanics, and that is today known as the cornerstone of what is called the postulates of quantum mechanics. So what I will now do is, as I move forward, I'll quickly remind you of the postulates. Again, I will not go into any detailed discussion, which we have done. Again, those who have attended the 4 to 5 class, we have done very detailed discussion of the postulates, but I will remind you of the postulates, and maybe I will ask some people to tell now. So can somebody state the first postulate of quantum mechanics? I mean, that is historically and traditionally accepted as the first postulate. Or you can say, no, that's the second postulate, but that is traditionally accepted as the first postulate, which we have taught. So can somebody explain, or not explain, can somebody state? Explanation is more complicated. Who will be able to state? So let me see how much you remember. Come on, I can see some of the faces who have got good marks also in 4 to 5. Can I start? Every state of a system is described by, well, so what happened? I mean, that's the first thing, right? The first thing is to remember the first postulate, because otherwise you can't start, right? So the first postulate shows that, so let me write down very, very cryptically. Again, I will not write in details. That every state of a system, now system, when I say system, of course it's a quantum system. That is obvious, because we are looking at postulates of quantum mechanics. So quantum system, the system can be a single electron, system can be a collection of atoms, single collection of molecules, and so on, whatever we defined as quantum. Okay? Every state of a quantum system is described by a wave function. It was called actually a wave function by Schrodinger, by wave function, and the standard nomenclature was psi. Of course, you are allowed to give any other nomenclature. The psi is usually a function of either coordinates or momenta of the systems. Remember, these are not measurement of the coordinates. As I told you, delta x, delta p is greater than or equal to h cross. So you can't actually measure the position. But this is only a variable of the functions. So this psi could be the position, so x1, x2, etc. up to xn. Let's say this could also be momentum. We have not discussed that. The standard quantum mechanics actually is based on the position representation or coordinate representation, and that's why we call it the coordinate representation of quantum mechanics. Of course, there is a momentum representation of quantum mechanics, which is a Fourier transform of this representation, which will not go into this, but this is the most standard representation. Then the interpretation is that the mod psi square is now says the probability density of finding this system at x1, x2 to xn. So now you can see how this connects to the uncertainty principle. We are merely saying that there is a wave function for every state, But now we are saying that if you take a mod psi square, that will be also a function of x1, x2, xn. That will basically be the probability density of finding one particle at x1, another particle at x2, another particle at x3, and so on. Nth particle at xn. So now that we have said the probability density, this is a very important term, it essentially attests to the uncertainty principle. That means we are acknowledging that there is an uncertainty. We can't find the electron. We can only say what is the probability of finding the electron at a particular point. Okay? So although there is an uncertainty, there is a probability of finding the electron at a particular point. So that is what we are acknowledging. So you can see that the very first postulate actually acknowledges the uncertainty principle. Okay? It doesn't say that the first electron at x1, second at x2, third at x3. The interpretation of this is very, very important, that the mod psi square, so this essentially is a function which is a probability function of getting an electron at x1, x2, x3. Again, remember, since electrons are indistinguishable, in fact, all quantum particles are indistinguishable. I hope you know that the quantum mechanics and classical mechanics, one major distinction is, apart from the size, that the quantum particles are indistinguishable. So since it is, we can't say that the particle 1 is at x1, particle 2 is at x2. We can only say there are n particles whose positions are x1 and to xn, and the probability of finding that is mod psi square. We are not saying that they are actually there. Again, I repeat, because many people get confused. We are merely saying that the probability of finding them at x1, x2, xn is mod psi square. So if it is a one particle problem, so let's take a single particle problem, and that is a very nice model problem. Single particle in 1D. So then, of course, I can write that as a psi x square, and I can say mod psi square, which is nothing but psi x of star psi x, is the probability density of finding that quantum particle. It could be electron, it could be boson, could be something else, of finding the particle at x. So some mod psi squared would then be defined as a probability density. Remember, each time I am writing probability density, and I will define it, what that density means, of finding the particle at x. Okay, if it is one particle. So that is mod psi square, which can be written as psi star x psi x. Note also that when you are talking of a quantum mechanics postulates, we have not said specifically if these are electrons. Postulates are of quantum particles. So quantum particles are small particles in that region which follow quantum mechanics, which are indistinguishable. That is important. Okay, at this point, we have not distinguished electrons or fermions or bosons. Okay, so some of these postulates are identical for that. So what does the density means? So density is essentially means that this is the probability per unit volume or length. Okay, so when I say the mod psi square, let's say this is P of x. So the P of x is the probability of finding in a unit length around x. Okay, how do I do that? Because as x changes, of course P of x will change. So what do? You use the convenient way that we do in calculus, that you take at, let's say, x equal to x0, the value is P of x0, the probability density. Then if I write this from x0 to, let's say, plus delta x, which is an infinitesimally small quantity, or let me write this as the infinitesimal delta x, then I can assume that within this delta x, the probability density is constant because it's a very small amount. Then I will say that the total probability between x0 to x0 plus delta x is nothing but P of x0 into delta x. Is it clear? So P of x0 is defined as the probability density at x0. So this is my probability density. So at x equal to x0, I define P of x0, which is psi of x0 square, mod psi of x0 square, sorry. So then I say that the total probability of finding the electron or the quantum particle between x0 and x0 plus delta x would be the probability at x0 times the delta x, because this is now the length. So this is total probability divided by the length. So that is how the concept of density comes in. So if you look at now the why it is called density, that P of x0 is nothing but total probability divided by the length. Okay. So of course you can define that as a density, and then we can write in the same manner the probability of finding the particle between two finite distances. So for example, if I want to find the particle P between A to B, where A and B are of course large separated, not like x0 to x0 plus delta x, then you have to do this as a mod psi of x square dx, sorry, mod psi x square dx between A to B, just like you do in calculus. So essentially what we are doing is that we are starting from A, dividing into infinitesimal thing, A to A plus delta x, etc., and then integrate between A to B. So just like you do in calculus, the whole idea of calculus integration, we actually bringing here. When A and B are now separated by a finite distance, okay? So it could be between here to a larger distance. If it is infinitesimal, you don't need to do, because you can consider it uniform. So you simply multiply by the volume element, and that is where the density concept of density comes. So I hope everybody clear, because this is a very important concept. Many people confuses the mod psi square as a probability. It is actually probability density. So you must understand the subtle difference between probability and probability density. Probability can be defined as a total probability between certain regions. Probability density is at a point. So you can't define at a point what is a probability. There is no meaning. So if you give a space, if space is infinitesimal, then you simply multiply. If space is finite, then you have to integrate. So that is very important to understand, that how do I calculate probability from probability density. So the interpretation that came here, and this was actually originally given by Max Born, another celebrated physicist. The interpretation of psi was the mod psi square as probability density. Now again, we are writing this for one single particle. You can easily generalize this for the n particles. N particle in one dimension, n particle, each of them in 3 dimensions, whatever. The generalization is very easy. Integrations will have many dimensions. That's all. So you can keep doing that generalization. So this is actually the postulate 1, which is very important, and it actually syncs with the uncertainty principle, because we are already bringing in the concept of probability density. All right, so it is already bringing in that concept, and we are essentially saying that the quantum particles cannot be located. So it's a very important part that comes in. Now, can somebody tell me the next postulate? Huh? Yes. Good. So every dynamical observable which are observables in classical mechanics. See, I can see that if I give you problem, you are very good. If I ask you to solve immediately particle in a box, you will do it. But this is not a problem, this is an articulation. And that is where there is a weakness. That if I have to articulate what is it, because that is very important. Problem solution you can all do if you are reasonably good in maths. But maths, I again repeat, excellent maths does not make you a good physicist. I repeat it. A good physicist can be a poor mathematician, because the good physicist has to have the concepts. Now somebody can bring the language. Mathematician, remember, mathematics is a language. So it is like you know something you are not able to explain. Okay? Many of you are actually good in mathematics. Now I am realizing. But you have to be good in physics. Okay? Because quantum mechanics is a subject of physics. In fact, I don't mind if you say, no, I know exactly what to do. You have to solve the difference. I can't solve the differential equation. I don't actually mind. Provided your entire framework is very clear. You know, that's something you can learn. But I can see that after doing the full quantum mechanics course, you're still struggling to tell me the postulates. I'm not saying that you're not telling, but you're struggling to tell. That's the word I will use. Okay? So every dynamical observable, which are defined in classical mechanics actually, is represented by an operator which I now call it quantum mechanical operator, which I just call quantum mechanical operator, but actually it's an operator. And for all measurable observable, these operators are Hermitian. So that's another important thing, that all physical observables which I can measure correspond to what I now call Hermitian operator. Now here comes a little bit of mathematics to know what is an operator. What is an operator? An operator acts on a function to make another function. So that's an operator, and those are Hermitian operators. So Hermitian operators have some special properties. Can somebody tell me what is one property of Hermitian operator? Self-adjoint, very good. So Hermitian operators are self-adjoint. What is adjoint? So let's say an operator A, I again repeat, acts on a phi to create psi. I am using what is called the Dirac notation. Again, I hope all of you are familiar with this. This is basically a function of whatever variable. This is also a function of whatever variables, and the function is represented as a notation ket, which again is something that we are going to use. So I again repeat that people who have not done Dirac notation, we have done it in the last class. Please get yourself familiar. Okay. So this is the normal notation. It will be written A operator acting on phi of whatever is the coordinate. Let's say x, to give you a psi of x. So this is actually written in this language. Okay. So the coordinates x, y, z, or x1, x2, xn, whatever, is actually silent. Okay. So whatever coordinates are there here, the same coordinates are here. So we don't need to write. So this is called the ket vector. So this is the Dirac notation. So we said that if A of phi gives you psi, then the adjoints are defined in the following manner, that the conjugate of phi, if you act adjoint of this operator from the right, you get conjugate of psi. So the question is, if I have a function phi, the operator acts on the left to give you a function psi. If I have a conjugate of phi, then the definition is that the adjoint of this operator, if it acts on the right, it gives you the conjugate of psi. So this is called the adjoint, and of this operator A, and the Hermitian operator, this A is equal to a dagger. So I don't have to write a dagger. So that is why they are called self-adjoint. So Hermitian operator, so for Hermitian operator, A equal to a dagger. Okay. So this is how the quantum mechanics platform is defined, because so far we have only defined a state of a system and how to define the probability density. The question that now you will beg is, how do I make measurements in the system? What happens? So for that, this postulate 2 actually prepares you that for every observable there is an operator. Then the question is, what do I do with this operator? How do I still measure? It still not answers the question. So that will come in the next postulate, which is the postulate 3, and that's a little difficult postulate, but it just says that, can somebody state this postulate? Anybody can state? How do we make a measurement after that? So if I have a state of the system psi, and if I have an observable to measure for which there is an operator A, then what do I do? So first of all, what does the postulate says? It says that if I make a measurement of A, of that observable, let's call it A, okay, whose quantum operator is A hat, okay, then this measurement always leads to, and that's a very important statement, the eigenvalues of the operator. Remember, every Hermitian operator has an eigenvalues. Okay, every operator has an eigenvalue. Every Hermitian operator also has an eigenvalue. What is an eigenvalue? Who doesn't know what is an eigenvalue? Everybody knows what's an eigenvalue? Engineers must be knowing, of course. The physicist, the chemist. Okay, fine. Then I don't need to worry about it. the eigenvalues for Hermitian operators happen to be real. So that's a very important definition. So all the measurements always lead to real values. But I'm saying that it leads to any one of the eigenvalues. I don't know which one. So this brings a very important question, that how can I say which one? This question was actually answered. It says that in general, you cannot say which eigenvalues you get, but you will get some eigenvalues unless the state psi happens to be an eigenfunction of the operator A. So if the state psi which I am measuring, on which I am measuring the A, happens to be an eigenvalue, eigenfunction of the operator A with an eigenvalue small a, then of course the measurement will always lead to eigenvalue A. This will always lead to eigenvalue. If it is not, then it will lead to some other eigenvalues. And that is a very complicated state, but these states are fairly simple states because their behavior is very much classical, that at least when I measure I get a same value, and these states are called the stationary states. So these are called the stationary states. So I can have also a stationary state of energy, which means if energy operator is Hamiltonian, then the stationary states are defined by states which are eigenfunction of the Hamiltonian operator. Is it okay? So this is, for example, the stationary state of energy. All right. So if I can define these states which are eigenfunction of the Hamiltonian, I define what are called the energy eigenstates, where measurement will always lead to EI for a given psi I, and this is very famously known as the Schrodinger equation. Okay, but this is actually a stationary state of energy, and we are more interested in the stationary state of energy because energy plays a very pivotal role in physics and chemistry. All of you know why energy plays, that is because of the thermodynamics. Thermodynamics is governed by free energy and so on. That is the reason we are biased by the stationary state of energy. But note that every observable has similar stationary states, where that particular observable will be measured with a certainty that this is the value that I will always get. Why I am talking of this certainty? Because the very important part of quantum mechanics actually leads to the states which are non-stationary. So for example, I look at a state psi which is not an eigenfunction. Let's say psi is not an eigenfunction of Hamiltonian to start with. Okay, so let's assume this. So this is the concept of what I call the non-stationary states. Correct? Because it is not an eigenfunction of Hamiltonian, and I want to measure energy. So I want to measure energy in this state. What will still happen? Let me, just for the sake of symbol, let me use these as some other symbol phi, because I have already used psi as eigenstates of energy. So let's say phi, which is not an eigenfunction of energy, and I may want to measure energy. Then what will happen is that I will still get one of the EI, because the first thing that I wrote, it leads to always eigenvalues of the operator. Eigenvalues of this Hamiltonian is of the EI. So I am going to get some EI, but which one? I can't tell. If it was a stationary state, I can definitely say I will get that particular eigenvalue. But here I can get E1, E2, E3, any of them with some probability. Now note that these non-stationary states evoked a serious concern of quantum mechanics, where Einstein had serious disagreement. It says that I have a state which is not an eigenfunction of Hamiltonian, but so what? I have a state and I make a measurement of energy, I don't know which value I am going to get. I mean, that will never happen in classical mechanics. So this was a very nice experiment, what is called the Gedanke experiment, which was actually done. It says that if I make an identical systems, hundreds of identical systems, thousands of identical systems, and if I make a measurement is done by robots who don't make any error in measurement, they will still get different values, which is one of the most I would say, disruptive thoughts in quantum mechanics, that how can this happen? Because if it is identical system, robots will always get the same value. And remember, this is not because of experimental error. This is inherent in the theory. This actually, the non-stationary state actually caused serious pain and serious discussion in quantum mechanics till, of course, Schrodinger said, although they will get different values, what I can predict is the probability with these values will come. How will the probability come? In the following manner, if I can always expand this phi as a linear combination of the actual eigenstates of the Hamiltonian. It is always possible in mathematics that a function can be expanded in terms of a complete set. And remember, Hermitian operator eigenfunctions form a complete set. So I can write this as a linear combination of psi. And then what was related is that the mod Ci square is the probability of obtaining a particular eigenvalue Ei. So this is a concept which was known as the superposition of states, and it's a very, very important concept, which actually I just called it postulate 4. It doesn't matter what is the number you give, superposition of states. So superposition of states can actually explain many of the non-stationary states. Okay, but these coefficients are now, square of the coefficients are now related to the probability. Just like in the first postulate, mod psi square is the probability density. So that is the reason the square is very important, mod Ci square. In fact, we showed in detail how it can be done. And in fact, in all such cases, for a non-stationary state, the way to obtain a value is through what is called the average value. And that brings in the concept of average value, or sometimes we call it expectation value. Right? So it says that the average energy in a state is integral psi star h psi volume element divided by psi star psi. If psi is not a stationary state, because then we have a probability of values E1, E2, En with mod Ci square is the probability, and one can show that the average E average is nothing but integral psi star h psi. In a Dirac notation, sometimes it is written as H average equal to psi h psi by psi psi. The denominator comes because I am assuming that it may not be normalized. If it is normalized to unity, then of course the denominator need not be written. So this is a very, very important concept, the average value concept, by which a non-stationary state could be written. Note again, in our previous class, I had shown in detail how this comes. By expanding psi in terms of the Ci phi I, Ci psi I, and then showing that the psi I is an eigenstate of H with eigenvalue Ei, one can easily show that this is nothing but, this H average is nothing but sum over I mod Ci square Ei, which is what my probability should be. Note, because I am getting all the values of Ei with a coefficient with a probability mod Ci square. So what would be the arithmetic average? Is like a weighted average, sum over I mod Ci square Ei, which I showed in the previous course that this is nothing but this. I hope all of you will be able to do this. Just stick in the psi and psi star, so that I could ask in some exam how to get this value. Okay, so that's an average value which I had actually shown in the class. Please remember, all that I am doing is just a rehash, an overview of what I did before, and I think it's important to do this in the very first class at least. And so then it almost puts the framework of stationary as well as non-stationary states of quantum mechanics. Yes. Well, I will not worry about it, but to give you an answer, if the same measurement is repeated, then they will always lead to the same value. Because this is a very, very difficult interpretation of Dirac. It says that after you make the first measurement, each state gets converted to its corresponding eigenfunction. See, for example, if somebody may get E1, somebody may get E2. The person who gets E1, for whom the state will be converted to psi 1. And once it is psi 1, now it is a stationary state. So it gets stuck. So this was an absolutely mind-blowing interpretation, which Einstein said this is absolutely stupid. Because depending on the observer, some state is going to psi 1, some state is going to psi 2. You don't know which observer will get what also, because it's a probability. This is an absolutely mad kind of theory. So he never accepted the theory. In fact, that is one of the reasons he never accepted the theory. But that's how the Dirac interpreted that once I make a measurement, the person who will get E1, for him, the system will be locked to psi 1. So essentially, it brought in a new concept of what is called the subject-object interaction. Depending on the subject who is measuring and the object, the interaction throws it to another state, which is always an eigenstate of that operator, and then it stays there. Once it is an eigenstate, no problem. So this part is very beautiful, the concept of stationary state, because this is like classical mechanics. Once you have locked a state into a stationary state, then you have no problem. The question that is also very important is that can I have a stationary state for multiple operators? That is, I calculate energy, I calculate angular momentum, I calculate dipole moment, many things. The answer is yes, if those operators commute, mutually commute. So that is where there is a very interesting theorem which says that if two operators commute, they have simultaneous eigenfunctions. Again, we had discussed this theorem in detail. If two operators, which is basically Hermitian operators, of course, they have simultaneous eigenfunctions. Now, very clearly, you can see the simultaneity essentially means that, right? Simultaneous eigenfunctions. Essentially, this means that if I have one state which is an eigenfunction of one operator, then another operator which commutes with it also can be measured with certainty, because it is an eigenfunction of both the operators. So that's a very important concept that we bring in, the simultaneity of measurement. And in fact, this is very important part of quantum mechanics. But don't forget the non-stationary quantum mechanics. This is something that is very important, and it is resolved by what is called the superposition of states. So this is basically superposition of states. It's very important. Most of the quantum chemistry, I now repeat, that we will be doing, we will be interested only in the stationary states of Hamiltonian. So this is what is important, but I must say this because this is a very important part of quantum mechanics, but we will actually be interested more on this. How do you solve this for a given Hamiltonian? So this will be our quantum mechanics for many particle problems. This is what this course will contain. We have already solved this for various one-dimensional problems, exactly solvable, even 2 dimensions, 3 dimensions. I will come to that. When can I solve it exactly? All right. So I think today I will stop here.